Morning. So thank you so much to Uli and Malcolm for the invitation. I'm thrilled to be here. So about a month ago, I was reading through Twitter and there was a comment by this hematologist, David Steensma, that was answering the question of how his medical center, this is Dana-Farber, chooses which trials they're going to run. They get a lot of pitches of clinical trials, but they actually have to select from a small number to actually decide which ones they're going to enroll patients from in their center. And so he went through a couple different reasons, but one of the most prominent reasons he gave was that the molecule had to be interesting and potentially safe and effective. And he said this is a really, really hard judgment, but it's something really, really critical in deciding whether to run a clinical trial. And so what he's describing here is something that goes on pretty much at every medical center when they're running a trial, and for that matter, it's going on inside the head of any investigator. Any number of trials we could be doing, which trials are we going to do? Now, normally you'd say, well, let's do a systematic review, see where the evidence gaps are, and then design a trial that's going to plug that evidence gap. But there are whole swaths of medicine where systematic review isn't really going to help you, or at least the traditional systematic review. For example, if you're testing a new drug and all you have is preclinical evidence, or maybe even phase 1 evidence, there isn't really enough information in the same format to aggregate in order to at least meta-analyze and estimate how much residual effect there is to detect. And so essentially what's going on in that setting is that you have very different kinds of evidence streams that you somehow have to integrate: preclinical studies, case reports, basic science, maybe trials of related drugs. Integrate that into a view about what the clinical promise of a new drug is. And the question I want to ask, what's at the center of this talk, is how well do we do? How good are decision makers at making inferences when they're dealing with diverse data sets about the clinical promise of new drugs? First, I want to talk a little bit about inference and research quality and how this question I'm trying to answer connects with the broader research quality question. So first, when we think about research quality, when we think about reproducibility, whatever you want to call it, waste, normally we kind of divide the research cycle into 3 different segments, and we've identified any number of different problems or deficiencies at each one of those steps. So with respect to design, there's now a huge literature showing frequent failures in the way we design clinical trials. For example, the excessive use of surrogate endpoints in trials that are leading to registration of FDA-approved drugs. Also, there's a large literature on reporting, deficiencies with reporting method of randomization, say, inadequacies in reporting of adverse events, publication bias. Again, a voluminous literature describing some of the problems with reporting. But you can have a study that is designed really, really well, and that is reported really, really well, and if the user misinterprets that study or forms some kind of inaccurate inference, you still are stuck with the problem of research waste. That person's going to make a decision that's not a good decision. That's not a decision that's really based on good evidence because they've misread it. And similarly, you can have studies that have a really crappy design and crappy reporting, but if you have a savvy reader of that evidence, maybe they know something about the low quality of the researcher, whatever it is, and they know to take that study with a grain of salt, or they know how to interpret it, then you can also have accurate inferences. And so really, it's critical to close off that life cycle if we're going to try to think about sources of research waste, to think about how actual findings are being taken up and interpreted, and then applied in the redesign of clinical trials. And that, in my opinion at least, is the bottom of the iceberg when we talk about reproducibility, waste, et cetera. Reporting design are really, really critical. It's great that we have a literature in those areas, but they're all things that you can see. It's fairly easy to study reporting because you just go to published reports and you see what's there and what's not. Same thing with design. The problem with studying inference and uptake is that mostly it happens inside our heads. It's a psychological process. And so it's extremely difficult to access in a way that is rigorous and reproducible. The bane of my existence, actually, as I'm going to describe. And so really what this talk is trying to do is to kind of map some of the underside of that iceberg. Now, I'm not the first person to note how important inference is with respect to research waste or reproducibility. I'll just go through a couple examples of the ways people have tried to get at this. One of them is using citation networks. This is a paper by Stephen Greenberg. That's great. The problem is that citations have any number of different motivations besides what's going on in an individual's head about inference, and so it's a very indirect measure or a proxy for what a person might be thinking when they cite previous literature. Benjamin Jobegovich has done all sorts of beautiful studies looking at the distribution of outcomes in clinical trials, odds ratios, say, finding, for example, that there's a symmetrical distribution of odds ratios around a null effect, and you use that to make claims that researchers are in clinical equipoise, which is a mental state, before they launch clinical trials. It's beautiful work, but actually, these distributions, there's any number of different reasons why you might have this distribution other than a particular belief state of researchers, a state of equipoise. So again, this is a really, really indirect way of trying to measure inference in research. More directly are some of the kinds of things that Isabelle Boutron and Philippe Raveau have done, looking, for example, at what happens when you expose researchers to abstracts that have spin. It seems to have an effect in terms of the positivity with which they interpret findings. And also more direct are work that actually one of their former students has done, a person named Ludovic Twinkart, who looked at how oncologists interpret odds ratios and found that oncologists are prone to misinterpreting the odds ratio, that there might be better ways of communicating about the benefit associated with cancer drugs with other metrics besides odds ratios. But by and large, this is a fairly thin literature at looking at what researchers and other decision makers take away when they read findings, whether they're well-reported findings or not. And so now I want to talk a little bit about some of the work that my team has been doing over the years to look at how researchers interpret and take up and make decisions around research. Now I want to say a couple introductory remarks about the method that we use. We use forecast method. It's a complicated method and it's probably unfamiliar, so I want to say a couple things so you have some context. So when I say forecast, what I mean is an explicit probabilistic statement about a verifiable future event. You can ask someone to predict something, but unless you can verify whether that prediction actually occurred, it's not particularly useful for these kinds of studies that I'm going to describe. So all of us know about forecasts from the realm of weather. We every day hear weather forecasts. So I'm going to go through what forecasting is like for weather. So if you're a weather person and you think there's a 100% chance of rain, it means that there's absolutely no uncertainty in your weather forecast. Likewise, if you say 50% chance of rain, means that it's a coin toss. And after a weather forecaster makes a series of different predictions, you can take those predictions and put them aside next to the actual outcomes of the weather to determine just how skilled that weather forecaster is. And there are a number of different components to measuring that weather forecaster's skill that I'll get into later in this talk. But that's the basic idea. One of the main ways that you score their prediction skill is by measuring the deviation from their forecast to the actual event, squaring it, and then taking the average. It's called a Breyer score. Weather forecasting is a bit like the kind of problem that I started off with, where you're trying to decide which trial to run. It's not like that today in an era where we have pretty sophisticated computer models, but it was like that back in the 70s and the 60s. You'd have one weather model and another weather model, a third or fourth, and you had some expert, a meteorologist, who had to sort of piece together which weather model to rely on or how to interpolate between the weather models. And essentially that's what's going on when you're trying to combine preclinical, clinical, as well as case report information. Okay, with that preliminary, let's get into some of the studies that my team has done. The first is a study that's looking at how well oncologists can predict the outcomes of clinical trials in their research area. So the idea here is that we took experts in 3 different cancer areas, general urinary cancer, lung cancer, and colorectal cancer, gave them 5 clinical trials that had not yet reported results, and asked them for a prediction of the probability those studies would meet their primary endpoint with statistical significance. It's a 30-minute survey. So the form of the questions they're getting is, what's the probability that your trial X, which is in your specialty area, will demonstrate a statistically significant result on its primary endpoint. We picked trials that were late phase and randomized and that were expected to announce results within a year so that we could verify the accuracy of their forecasts. And we picked experts who were pretty clearly experts. They had published at least 3 articles in the disease area that were available on PubMed, or they were affiliated with top-ranked U.S. centers, cancer centers for their area in cancer, Canada, not cancer, the UK and Australia. So we invited 806 participants, 137 participated. Here's the demographics. You can see about mean age of 48 years. H-index 24, so these are fairly productive, somewhat on the young side of cancer experts. Primarily, this is a North American sample. And here's a distribution of what their actual predictions look like. So a 0, is this working? Yeah, there we go. So if you're on these are 3 different cancer areas here. Ooh, it's hard to point with this thing. Okay. It's like pointing in a mirror or something. All right, so 0 would mean that they are certain the study's going to be negative. A 1 is that they're certain the study's going to be positive. So you can see right away, I'm telling you, this is really going to take skill to point. So you can see right away that a lot of the predictions on all 3 of these tend to be clustered towards the 0, which means that they were generally pessimistic about studies being positive. So contrary to our expectations that researchers are massively prone to optimism bias, we've never seen anything like that in any of our studies. In fact, they're unduly jaded. They're very, very pessimistic about outcomes. So now we're going to apply the Breyer score, because we have the results of those trials, to see how skilled they were in their prediction. And when you do this, you need a benchmark to compare the quality. And the easiest benchmark to use is the 0.25 benchmark. That is the Breyer score you would get if every time I asked you for a prediction about a clinical trial, you said 50%, which is the equivalent of not really making a prediction. It's the equivalent of almost abstaining from making a prediction. So it's your maximum uninformed prediction. A better prediction benchmark, a little bit more sophisticated, would be to go with base rates. We know that 30% of phase 3 trials are positive on the primary. Maybe it's 35% for phase 2 studies. So if we combine those, with a simple algorithm in the trials in our sample, you should be able to beat 0.19 based on that really stupid base rate benchmark. So this is actually what the distribution of outcomes looks like. You can see on the top, 59% of the individuals here forecasting did worse than if they had just hit 50% all the time. That's pretty clear indication of what's called overconfidence. They're giving numbers that are way beyond where they should be. It's not over-optimism, it's not necessarily over-pessimism, but it is overconfidence. They're using too much of the range of probability. Now you can break this down and look at particular skills, and this is a little bit depressing. One of the skills is called calibration. That's the extent to which if you offer a probability a certain number of times, that event will occur, that same frequency of times. So if you say 20%, 100 times, 100 of those events will have occurred 20% of the time. And so if you have perfect calibration, that's the curve on the left, you should have a curve that goes right along unity. And you can see the actual measure is not going anywhere along unity. This is a ROC curve. Everyone here probably knows you want maximum area under the curve. Here you can see there is minimal area under the curve. So there's really no ability to discriminate by offering higher forecasts for trials that have positive outcomes versus lower ones. So there are a couple conclusions we can draw from this study. Number one, experts tend to be fairly pessimistic about trial primary outcome attainment. You might say, well, this is the nature of research. They're all in clinical equipoise. They're uncertain. You're just showing that this is unpredictable research. No, that's not right. We're showing that there's actual deficient skill with forecasting, because if they were just in clinical equipoise, they should be able to beat the 50% benchmark, much less the 0.19 benchmark. So here, this really is a problem with generating numbers that are accurate predictions. There are some major limitations in this research. Number one, the forecasters didn't have access to the whole protocols. They were basing the predictions on clinical trial registration records. The predictions were collected relatively late in the period of the trial, so they could have had inside information, although it didn't seem to have helped them very much if they did. It was a limited trial sample. Who knows if we did this in another set of 5 trials for each one, whether we would get a similar result. But I think the most important one is that when you ask people for probabilities, it's really hard to generate probabilities, and many people are unfamiliar with elicitation. You would think people who design trials and who are working with the language of probability would be pretty good with this, but the fact is it's really, really hard for people to, unless you're really experienced with elicitation, to give good numbers, and I think that's an important limitation of this work. So that was led by my postdoc, Danny Benjamin. Okay, so that's project one. Now, the next project is looking at neurology clinical trials, and here we're using a very different method. This was actually done when I was on sabbatical here in Germany. So instead of asking a binary prediction, what's the probability this is going to occur, a simple binary event is going to occur, instead what you're asking is for a probability of occurrence across the range of possibilities. So let's say if you're up, oh, come on, make things easy for me. All right, let's say, there we go. So let's say you're talking about the probability, the proportion of patients that will be alive at 6 years or at 1 year, and let's say it's an ALS clinical trial. You would start by asking the person, what's the lowest proportion you expect to be alive? What's the highest proportion? So they would start by saying maybe 20% and 50% is their range. And you would give them a bunch of other chips, 19 chips in this case, to fill in a whole distribution. And what that's capturing is what their belief is for various outcomes across the entire range. And so you can take that now, and when you actually have the outcome, this dotted line here, you can score them using something very similar to a Breyer score for their accuracy. And here, instead of that 50% algorithm to score them, to benchmark their scores, here you use what we're calling an ignorant prior, basically a very flat prediction across the range from 2.5% to 97.5%. So here we took experts in 3 different clinical areas, gave them a clinical trial that had not yet completed, asked them to predict the absolute outcome for patients in the placebo group, which should, in a sense, be a clinical judgment because placebo groups in all 3 of these conditions are kind of the standard of care, and also the treatment group, and then obviously went on to score their prediction skill. So for trials, we wanted to pick late phase trials, randomized studies that would be familiar to a wide number of different people so that when we elicited them, they would know about the trials. And again, we needed to be trials that were going to close within a year so that we could get results to compare to score accuracy. For experts, similar to the other study, we needed to have at least 3 publications in the relevant disease area. In this study also, we recruited co-investigators of that clinical trial, people who are actually recruiting for the clinical trial. So these are the 3 trials that we used. There was a stroke trial that was testing natalizumab and immunotherapy, an MS trial testing vitamin D, and then an ALS trial testing a neuroprotective drug called rasagiline. And all 3 were private. All 3 studies were also negative. They were negative outcomes. This is sort of the fact, this is what it's like to work in neurological drug development. It's always negative. And you can see all 3 were published, well, 2 of them at least were published in pretty prominent publications in neurology as sort of a top venue. One of them was not published, but at least they posted the studies on clinicaltrials.gov. Here's the characteristics of our sample. Again, mean age of 46. You're going to see that number again and again. It seems like 46-year-olds really like to participate in my studies. The H indices, you can see here, show that you have a fairly productive group of stroke researchers, MS researchers, and the ALS researchers probably have to contend with the fact that the ALS journals have lower impact. Okay, here's a distribution of actual predictions that are averaged across everyone's distribution. Stroke over here, for example. There we go. So stroke, just to take one example, the black is the treatment group, the lighter color is the placebo arm, and these are actually, the dotted lines are the actual outcomes, the actual estimates, and the dark lines are the median predictions of each of the different groups. So you can see in stroke, they were massively off in their prediction. In ALS, you can see they were pretty close to being accurate. These down in the bottom are all measuring the median difference between their prediction for the placebo group versus the treatment group. So, so you can see that people, again, were pretty pessimistic. Their median predictions are pretty close to 0, so they expect there wasn't really going to be an effect of any of these drugs. And the actual outcome is this dotted line. So you can see there actually was a larger effect in the stroke study than they expected. There was a tiny, tiny effect for the MS study and a tiny, tiny effect in the in the ALS study as well. Now here's some good news. It turns out that people's predictions, well, let's start with the good news. For MS and ALS, most people's predictions were contained within, the actual outcome was contained within the 95% subjective probability interval of the forecasters. So it means they weren't completely off base. They weren't out in left field. The bad news is for the stroke researchers, they really were out in left field. Only 3.1% of them had predictions, their 95% essentially confidence intervals, subjective probability intervals, captured the actual outcomes. So really the stroke researchers in this study had absolutely no clue about what to expect for absolute outcomes. And I can explain why that would be. In terms of beating the ignorant prior, you can see here that generally they did not beat the ignorant prior. This is the score for the ignorant prior result, these dotted lines here. This dark line up here is indicating the median score. And so you can see clearly that, that there's a worse average accuracy at prediction than that ignorant benchmark. What we did do here is we aggregated and by averaging the forecast to see whether we could improve on individual forecasts. And not too surprisingly, given what we know about wisdom of the crowd, it turns out that you can improve predictions fairly dramatically by averaging predictions together and then using that one as the prediction. So we saw improvements for stroke, MS, and also for placebo of ALS, but not for the treatment arm. One last component to the study that's worth mentioning, we had two strata here. We were asking for forecasts for co-investigators as well as independent experts. And the co-investigators did no better or no worse, clearly, than the independent experts in terms of predicting outcomes. So maybe that's a reassuring because maybe it means that co-investigators don't have any privileged or distinct knowledge about outcomes of trials that they're running, or at least they didn't in this case. Okay, so again, many challenges here with limitations. Unfamiliarity with elicitation is a big one. But I think broadly here, I think we can walk away and say, well, experts were pretty good at predicting these were going to be negative results. But generally, in terms of predicting the actual evolution of disease across the trial, they did a generally pretty bad job predicting. And then there was no difference between independent experts versus principal investigators or individuals that were recruiting for the clinical trial. That work was led by Pavel Atanasov. Now, I'm going to run out of time, I fear. I'm looking at that clock, and it's menacing. I have a third study I want to report. I'm going to go through it fairly quickly just to give you a gist. So this third study is looking at how people make decisions when you present information in clinical trial protocols. So in a typical clinical trial protocol, you're describing the rationale for doing the study, and typically that takes the form of a narrative review. And we all know that narrative reviews tend to be prone to bias. They're very hard to reproduce. And the question is whether or not that narrative format biases decision makers that ethics reviewers or others might use to assess the clinical promise of the drug. And so the approach we wanted to use was a randomized controlled trial where we give people a narrative review versus a systematic review of the same information and ask them for a prediction and also ask them their willingness to give ethical approval for that study. So for this, we chose a late phase randomized controlled trial that was publicly funded and for which we had a very generous and gutsy principal investigator who was willing to give us her protocol before the study was reported and allow us to do a systematic review that might expose her narrative review as having been biased. This is a study that we used. It was a study that was testing extended tinzaparin in patients who had had resection for colorectal cancer. Our experts were recruited from mailing lists of experts who are surgeons of the colon and rectum, because that's sort of the specialty area. Here's a 2x2 table showing the characteristics of the studies that were in the commissioned systematic review, the one that we commissioned for this study, versus in the narrative review. And basically what you can see is that there are a lot of studies that are in the narrative review that were not in the systematic review. Those are mostly testing similar drugs, but not the same one. There are a couple studies also in the systematic review that were not in the narrative review. Those are mostly the smaller studies. By the way, these were all, our systematic review was censored so that it was done around the same time that the narrative review would have been done. Okay, so here's our sample. Again, 45-year-olds took our study and took our survey, just sort of going right to the results, not wasting any time. Here's a violin plot that's describing what their predictions were for the primary outcome. And here, absolute risk of reduction is what the measurement was. And so what you can see here is for those who read the narrative review, okay, where are we? Okay, on the left, you see the narrative review, and that red line is indicating the median prediction. On the right are those who read the systematic review, and that's their median predictions for the primary outcome on that study. There was a statistically significant difference between the people's predictions in the narrative review group versus the systematic review group. When we then went on to ask them the question, what's the probability that you would recommend a study for ethical approval, you also saw a significant difference, and the difference was similar, as you would expect. Systematic review readers tended to be much more skeptical that the study ought to go ahead and be done. There was, not surprisingly, a very high correlation between people's pessimism about the study and their unwillingness to approve of the study. Again, lots of limitations here. This is one clinical trial. Who knows whether it would happen for lots of different clinical trials. We don't know who's right. It's possible the narrative review people are actually right. We don't actually have the study ended yet. It's been not matured, so we have to be really careful with interpreting that. The other big limitation to mention here is it's really hard to isolate exactly what the causal component is of that difference. It could be the information in the systematic review. It could be the format of the systematic review. Who knows? But whatever it is, there's something in that systematic review that seems to have pretty robustly led to a clear difference. So the broad interpretation here, not surprisingly, is that experts are sensitive to evidence. What I want to emphasize here is it's not just experts, but experts who have particular knowledge in this area and who can embed the information they read in a narrative review into their own judgments. They too are sensitive to evidence formats. And their ethical judgments are also influenced by those assessments of evidence. And in this case, at least, the narrative reviews seem to lead to a much more clearly optimistic set of judgments. That work was pursued by Mike Yu. Okay, I'm on the last lap here. Let's go towards conclusions. What does all this mean? When I tell people I do prediction work in research, they're completely befuddled. Why would you do this? Why does this matter? Why do you want to know this? And I'm always completely befuddled by the question, why wouldn't you want to know how well people can predict outcomes in research? It is the medium through which we make decisions is prediction, in a sense, although we don't normally think of it. And so to me, it's really, really crucial. So I'm going to give you a couple examples of issues that I think our work highlights. Here's one. What's the quality of our clinical practice guidelines? Well, a lot of the recommendations in clinical practice guidelines are based on systematic review. But in many areas of medicine, at the frontier, there usually isn't enough trial evidence to aggregate, to form a good judgment about a recommendation in its systematic review. So in cancer, for example, upwards to 70 to 80% of the recommendations are made on very low level of evidence. A lot of them are made just based on either expert evidence, expert opinion, or a bunch of experts sitting around looking at a small clinical trial and deciding whether they believe it or not. If it's true that experts have a really, really hard time predicting, which my data seem to suggest, it suggests that a lot of the recommendations that are in those clinical practice guidelines may be highly fallible. So I think that's one take-home message here. A second one is the question of research priority setting, getting back to the beginning part of this study. You've got a bunch of trials, smoky room, people are sitting around trying to figure out which trials they're going to run. So you'd hope that people have pretty good skills about sniffing out and discriminating between the ones that are going to have a big impact and move the needle for medicine and the ones that aren't. And the data here at least suggests that they have a really, really difficult time doing that and that we probably have room for improvement. Research communications, I think this is really critical. Probability is the medium through which we communicate from one person to another our beliefs about outcomes. It's if you say something's likely to occur, does that mean 50%? Does that mean 90%? Probability is a way that we can render much more transparent what we actually mean. So if people have a really, really hard time using probabilities to come up with accurate predictions, it means that we're probably miscommunicating with each other a lot when we talk about risk and when we talk about benefit. Finally, quality of scientific training. I think there were a couple remarks, maybe in day one, about the need to teach critical thinking. It's great that we teach critical thinking. One thing we probably don't teach people what to do is prediction or the actual process of inference. We probably teach people how to read articles critically, and that's great. For example, if I were to ask anyone to predict the probability of any trial being positive, you should just immediately know right off the top of your head that if that trial has an alpha of 0.05 and a beta of 0.8 or whatever the power is at 0.8, you should know, like, don't pick 100%, stay away from those extremes, stay somewhere towards the middle, right? That's fairly sort of simple logic, and I think there's a lot that we can learn not just about how to use probabilities, but how to ratchet back our overconfidence when we start talking about probabilities. Generally speaking, people think they know much more than they do, and that's how you get those really, really bad Breyer scores. I will close by just reminding you, so I think that this is the bottom of the iceberg. There's very little we know about it, partly because it's so incredibly difficult to study this process. I'll close by saying, if this has intrigued you, if I've inspired you, I just want to warn you, do not try to do this research. It is backbreaking. I mean, it has practically killed me. So, and I can tell you later why. And it's also killed a lot of the people that I've had to work with. These are the casualties who I want to thank. This is the individuals who were involved in my cancer study. These are the individuals, including here Uli, who were involved in my study of neurology. And these are the individuals that were involved in the study of narrative review, of systematic review. And these are the funding agencies that have funded this work, and I hope will continue to fund this work in the future. Thank you.